Okay, hi. Welcome everyone to the afternoon sessions in the PPML workshop 2024. So today I have the great pleasure of introducing Nishanth Chandran. I visited last year in India. It was a great experience, and I'm very happy to finally be introducing him in person. And Nishanth is a principal researcher at Microsoft Research India, who focuses on cryptography, cloud security, and secure computation, among several other topics. I'm very much aware of a lot of his works, and I'm very happy to learn about what he's going to tell us today. He has previously worked at AT&T Labs and MSR Redmond, and he has received several awards, including the 2010 Charafaz Award, published also in top computer science conferences, and received major conference committees as well. So he got his PhD and master's from UCLA, and his bachelor from an university in Chennai. And something that is also very interesting is that he's a very prolific violinist who promotes Carnatic music. I was very happy to check out the YouTube videos, and I encourage you to do that as well. But probably this is also very fun. He's going to tell us today about practical cryptographic solutions to secure inference and private benchmarking. Thank you so much.
Thanks, Daniel. Thanks, Daniel, for the very kind introduction, and thanks to all the organizers for organizing this every year. It's a very fun workshop, and thanks for inviting me as well. The interesting thing is I've performed over here in the same hall 18 years ago, so it's kind of in a different avatar, so it's kind of interesting. All right, so today I'll speak about some cryptographic protocols for secure inferencing and private benchmarking, which I'll talk about, and a little bit about secure training as well. A lot of the work and slides are heavily biased by whatever work we are doing at MSR India, so I apologize that I'll not comprehensively cover the enormous work that is taking place in the practical MPC community, and stick to whatever we are kind of doing, but happy to chat about all of this offline. I have the unenviable task of being the first speaker after lunch, and I know many people are fighting jet lag, including myself, so hopefully all of us will be awake. All right. Okay, so let me quickly set context in terms of a couple of scenarios where we would like to use crypto to solve the problems we have at hand. These are essentially one and the same problem in different forms that you would see. Right? So the first one is what we call secure inferencing, or a private deployment of a machine learning model. So on the left over here, you have an entity that has pre-trained a machine learning model. And this machine learning model could have been trained on sensitive data. And therefore, the model weights that have been obtained from the training process are private information. And it's intellectual property of this entity on the left. And therefore, that's sensitive information that they don't want to part with. In today's LLM context, even if you're working with a public like an open source model, typically they come with a prompt which has been come up with like a lot of effort, and therefore considered IP by this entity on the left, right? So you have a machine learning model publisher on the left over here, and you have a model consumer on the right. This is a user. It could be a medical entity. You want to learn the inferencing of this machine learning model on some private input that you have, right? So, and so over here, in this example, patient data is sensitive, and you want to be able to compute inference results without sharing any information in the clear with each other, okay? Another interesting use case, which is kind of a generalization of whatever I spoke about in the previous slide, is that today there is a proliferation of models all over the place. Everyone claims that their machine learning model is the best by whatever metric, right? You come up with a metric and then claim that your machine learning model is the best on whatever parameter that you may want to claim it to be, right? And a lot of business decisions are based on these results that are coming out saying that this machine learning model is the best, right? And there are actually two problems in this space over here. One is that there is an acute paucity of good benchmark data. That is, I want to be able to test whether a machine learning model is good or not. So I want maybe like inputs and outputs, and I want to measure the quality of how the model is. And curating these benchmarks itself is a very difficult task. For example, It could require domain expertise. It could be that I may want to create benchmarks in different languages. So just curating them is something that's incredibly hard, right? And it could also be intellectual property because it is domain. If it's domain expertise, I don't want to maybe necessarily reveal all the data that I have, right? So that's one problem. And the other problem is that today what happens is that when I create a benchmark, I typically let it out in the open, and then people evaluate their machine learning models on that benchmark, right? That's like, I mean, for all the professors over here, that's like giving the test to a student like a week before and saying, okay, how much did you score, right? And even the answers, in fact, right? So that's something that really you don't want to do. You would like to keep keep the tests hidden from the machine learning model itself. And this problem is known as like contamination, where the model itself has been trained on the benchmark data in some form, shape, or form of the other. It may have seen the final benchmark data on which it's going to be tested on, or it may have seen some translated version of it. It could be something like that, right? And so one approach which we as cryptographers can say, we can solve this problem is if we could evaluate proprietary models on private test data sets, right? So again, it's a similar kind of feel. You have again a machine learning model owner, AI vendor on the left over here. And now you don't have just a single point, you have some test data set, right? This could be the benchmark data set that's going to be kept private, right? And now you may not even be interested in individual inferencing results. All you're interested in finding out is maybe just the accuracy of the model on that particular data set, right? Or it could be any other score that you're interested in measuring. It could be fairness, it could be whatever that you want to measure about the model, some metric that you want to compute, and maybe even check that if it passes a bar or not, right? So this is again another use case. And yeah, and finally, private training on joint data. So if I have two entities over here, you want to run a complete training process as if all of the data were centrally located in some place, not like federated learning, but you want to run the original training algorithm itself as if all the data is in one place, right? And so can you do this without revealing patient data to each other? So so these are three broad problems that we have been interested in trying to come up with solutions for. Okay, so let's just set context in terms of what types of machine learning tasks do we want to be able to run. We want to run like state-of-the-art models. We don't want to be left behind. If the machine learning gets better, we want to get better as well, right? So, so when we started off, things in the community of cryptographic solutions, this problem was much smaller than this, but things have advanced now, and so we started looking at something like CNNs for like lung disease classification, which is on the left. It has few million parameters. 3 giga floating point operations. This give you a sense of how many operations one needs to do to compute this this model. Slightly larger would be ImageNet classification, something like VGG16. And then all the way today, if we look at some of the open source models, if you look at the Meta's Llama model, 7 billion parameters. So we have moved up a couple of orders of magnitude over here, even larger number of parameters. And we want to be able to support all of these, right? And just to give you a sense of how fast is the really fast clear text algorithm, if I wanted to actually execute this today in the clear, how fast is it, right? So therefore, we want to come up with solutions such that the price of security is not terrible, right? So just to give you a sense of that, yeah, okay. Yeah, so VGG16 inference actually on ImageNet, if I take state-of-the-art like Hopper GPUs and I just take like PyTorch code and execute it on it, it's like super fast, right? Just even though you're running so many operations, it's like under a millisecond, right? And things like even Llama 2 is like about 50 milliseconds, right? So it's, even though you're running so many operations, it's fast, right? And so we want to be able to be in a position where we can tell people, if I'm using cryptographic solutions for this problem, it's not terrible, right? So where are we today? And we will see how far we have come and where we are going with all of this. Okay, so by now, most of you in this room don't need an introduction to how we will go about solving this problem. As cryptographers, we know that secure multi-party computation, or in this case, based on the examples I gave, two-party computation is something that's going to help us solve this particular problem, right? So in its most general form, you have n parties, T corruptions, Pi has input xi. The goal is to compute some function f that they agree upon on all of their inputs. And you want correctness, that indeed they compute the function correctly. You want security, that they learn only the function output and nothing else, right? So nothing fancy over here. This is old stuff. And as you can see, like all of these use cases that I described, secure inference, benchmarking, training, all of them are a special case of 2PC, right? So model publisher has some model weights on the left over here, which is W. Model M is the model's architecture, which we're assuming to be public and known to both participants over here. It's like the function description. And the model consumer on the right has some input X, and you want to compute M of W comma X. So standard 2PC should actually solve the problem for us. Okay. However, when we started working on this problem, I mean, there are plenty of challenges in applying it in the machine learning context. Number one, there's the problem of usability, right? So we cannot expect machine learning practitioners to be aware of secure multi-party computation. We can't expect them to write their machine learning algorithms such that if I were to run it on MPC, the cost would be low and so on. They're going to write their machine learning algorithms and it should work. And they will write it in the platform that they are most comfortable with, right? And we also don't want to do any kind of fine-tuning or retraining of models in the case of inference. If I'm given a model, it should work out of the box, it should work, right? So that is also something that we don't want to do. We want to support really large scale models. So we already saw that healthcare, LLMs, all of these are really large models. In terms of performance, I mean, if you look at applying MPC to this problem, if I start off in a very vanilla setting, communication of these, I mean, these models are so large that if I just calculate the amount of communication needed to compute some of these, could just go in like tera or petabytes also, right? So this is just, and it's just not going to scale at all. On the other hand, the clear text algorithms are only getting faster. You have better GPUs, computers getting accelerated, so on and so forth. And all of that is not really benefiting our MPC protocols because we are stuck with humongous communication overheads, which are not going to get better if I throw better hardware at the problem. Okay. So with that in mind, I mean, we have had a series of works, as I said. I mean, I'm speaking only about the work that we have done. There's been also other works in this area that I'll briefly touch upon. But the EasyPeasy system is kind of an end-to-end cryptographic system for doing any kind of practical, secure, two-party inference, benchmarking, training. And it's really easy to use in the sense that you can take any machine learning algorithm that you want to execute and run it through the system and get like 2PC code to execute whatever you want to, depending on the use case, without any kind of crypto knowledge. And we'll see that we are somewhat quite performant as well. Okay, so most of my time I'll spend on the cryptographic protocols, but I will very briefly cover usability and other things as well a little bit. So in terms of usability, there are broadly like three challenges when you want to solve the problem of usability. And this is not unique to our system. Our system also integrates some of these features. But the first one is that most machine learning code is written in floating point arithmetic. If you look at all the libraries, TensorFlow, Onyx, PyTorch, all of this. And if I want to emulate floating point arithmetic in MPC, it's very expensive. So on the other hand, fixed point arithmetic is a lot easier to emulate in MPC. And so it's nicer if we are able to have a clear text algorithm that works over fixed point. And so you may want to translate your floating point code into an equivalent fixed point, an algorithm that works over fixed point arithmetic that doesn't lose accuracy. That's kind of one step that needs to be done. And that's done automatically in the compiler that we have, right? The second thing is that ML code has several high-level building blocks, things like matrix multiplications and convolutions and all of these. All of these at their low level can be expressed as simple element-wise multiplications and additions. But if you were to do that, you lose a lot of context on what function you are computing. And because of that, you could pay severe penalties in terms of overheads if you lost track of what it is that you are computing. So that's something that is important to be aware of over here, right? So you want to have an MPC protocol for a kind of a circuit that has high-level gates, right? Things like matrix multiplications, convolutions, all of these, you want them to be gates in your circuit itself, right? And then the last thing, which was also briefly touched upon in the talk this morning, is that there are lots of transcendental functions which themselves have to be approximately computed, even in floating point arithmetic. And so you need some approximation of these functions. And because we collaborate very closely with programming languages folks, we have spent a lot of effort trying to get approximations of these functions that are both accurate themselves, not necessarily only accurate in the machine learning context, but precise in the context of the underlying function itself. And there's an accurate notion of what it means for the functions to be precise. So you want to have approximations of functions that are both precise as well as inexpensive to compute in MPC, right? So our team has spent some effort doing this, kind of coming up with approximations of functions that are crypto friendly, but also precise, so that you can actually like plug and play these functions into any application and you expect it to work well, right? Okay. All right. So for those of you aware of like MPC, 2PC, there are plenty of things like what is the computation model, what is the threat model, so on and so forth. I'll tell you a little bit about the model that we work in, which is also a couple of other systems also in the real world today are working in that model. So the model that we're working with is in what we call two-party secure computation with a dealer, or you can think of it as with pre-processing, right? And how does that work? You had these two parties, you had the model publisher and you had the model consumer on the right here. But additionally, you also have a trusted entity that gives correlated randomness to both entities over here, right? This is even before all inputs are known. This entity does not need to see any of the, does not get to see any of the inputs or anything like that, but just kind of gives correlated randomness, or I'll sometimes refer to them as keys to both of these entities. And that depends on the size of the function that you're going to be computing, right? And once that's done, this entity does not need to be involved anymore. And then the 2PC protocol takes place between these two entities as before, the model publisher and the consumer. Okay. So this is the kind of model that we are working with. It's somewhat natural as well, because anyway you have, if I'm offering MPC as a service, there's somebody who is actually setting up these machines for you to actually do this MPC computation. So it's not a stretch of imagination that that entity also sets up the machines with correlated keys as well, right? And we are not the only ones to kind of work in this model. There's Metascripten that works in this model as well. There's the startup Infer. I don't know if there's anybody from that company here that also kind of works in this particular model. So we also kind of are looking into this model of computation. Okay. Furthermore, for now we'll only consider semi-honest secure 2PC. I'll briefly touch upon the malicious case towards the end of my talk. And so to concretize it in the crypto world, how is it going to look? So you have a dealer over here that provides, in a pre-processing phase, provides randomness R0 and R1 to party 0 and party 1, and then goes away. And then in the online phase, party 0 gets some input X0, party 1 gets some input X1, and you want to compute f of X0, X1. Okay. And we are interested in the cost of this online phase. How fast is this online phase? How fast can we actually make it? Okay. Okay. So the protocol structure is, I mean, very similar to what you might have seen in any kind of many MPC protocols. You have a party on the left that has input X, party on the right has input Y, and there's an initial input sharing phase. Typically, you secret share your inputs according to some secret sharing scheme. And then after that, you have protocols for various gates or high-level functions in your protocol that take as input secret shares of input and get secret shares of output. Right. So that's kind of the protocol structure, and you'll do this for all the gates in your computation, and finally have an output reconstruction phase. Right. Okay. All right, and so we're just maintaining this invariant that all protocols start with input shares and end with output shares. All right, so now let's get into the interesting part, which are all the cryptographic protocols. Okay, so if I want to have secure two-party computation protocols for all of these problems that I spoke about, you can broadly categorize the types of functions that you need to support into quote unquote arithmetic and Boolean type operations, right? And by arithmetic, I mean things like addition, multiplication, matrix multiplication, convolutions, and so on and so forth. And by Boolean, I mean things like truncation, which is required because you're working over fixed point arithmetic. Whenever you multiply two numbers, the scale doubles, and therefore to go back to maintaining scale, you need truncation protocols. You need things like ReLU, which is just a fancy name for max of x comma 0. You need protocols for things like max pool, etc., transcendental functions. All of that you need protocols for that, right? Now, for the arithmetic computation in this particular model, when you have when you consider 2PC with dealer, essentially there's one class of protocols that that exists in the literature, which is Beaver based multiplication protocols. You can have Beaver based multiplication, matrix multiplication triples as well, and that has a big savings versus doing like element wise multiplication. But other than that, this is kind of the only kind of technique out there and the fastest technique that can compute these types of functions. So in this model, all the interesting things happen in the Boolean world. And here there are many options. I mean, for those of you familiar, there are either garbled circuit-like techniques that one could consider. There are secret sharing like or GMW-like protocols that one could consider. And then there is a very recent paradigm, which is function secret sharing based 2PC protocols that one can consider. Okay, so most of what I speak about will be about this last one, the FSS based 2PC protocols, and I'll briefly compare and contrast them with how they work against the secret sharing and other protocols. Okay. All right. So function secret sharing or FSS is a very nice primitive introduced by Boyle, Gilboa, and Ishai in 2015. And it essentially does the following. It kind of is you can think of it as a dual of MPC. MPC was working on secret shares, this kind of, and assume the function to be public. This kind of does the opposite. What it says is that you can take a function f and you can split it into two shares, f0 and f1, okay, such that if the two parties agree upon some common input x, right, then they can locally run some computation on that x. So party 0 can compute f0 of x, party 1 can compute f1 of x, right? And somehow locally they would have gotten, let's say, arithmetic shares of f of x itself. Okay, so the total local operation is what FSS kind of enables. Okay, and these two values f0 and f1 are known as the FSS keys. Okay, this is the correlated randomness that needs to be given. Okay, so correctness requires that for all x, you want f0 of x plus f1 of x is indeed f of x. So you end up with arithmetic shares of the output. That's what correctness says. And security requires that if I look at each of these keys individually, it hides f in some sense. We will see what it means to hide f, but it hides some property about f. Okay? There's some secret that remains in f. Okay, and you want f sigma actually to be compact. You don't want it to be exponential in the input size. And we know now protocols where you can have this in like where f sigma is like much smaller. It's like polynomial in input size, right? So that's kind of the non-triviality of it. Okay, so now I presented FSS, but how does that relate with two-party secure computation? Again, the same set of people showed how this is feasible, how you can construct a 2PC protocol in this pre-processing model via function secret sharing, right? And the high-level idea is as follows. Assume that now this is a circuit that you want to compute, right? For now, let's just assume that all wires carry like ring elements, okay? What I do is that I look at a particular gate. Let's say this is the gate that is supposed to take, it's just a unary gate, let's say it takes as input x, right? And it has to output y. This gate f. What I do is I consider what is known as the offset gate for the same function. And the offset gate for this function denoted by f hat does the following. It has embedded in it two secret values, R and S. Okay. And it takes as input not X, but X hat, which is X plus R. Okay. So it is X. So wherever I say plus over here, there is an inherent like modular arithmetic. It's all happening over the ring of integers, let's say mod 2 power 32 or 2 power 64. But I've dropped it everywhere from the notation. Right. So you have X hat. This function takes as input X hat, right? Computes X hat minus R, then computes F on it, and then again masks, that's what we call in this word, and masks the output with some S to get Y hat. Okay. So you consider this, this function family, and let's say you had FSS protocols for this function family. Now, how could you use that to actually construct 2PC protocols? We want that the FSS protocol that you construct, we want it to hide these two values, R and S. We want it to be hidden. Okay, that's the property that we require from the FSS protocol. Okay. So now what we do is we take every gate in our circuit over here, and correspondingly we get the offset circuit as well. Okay. So now what happens is that to get 2PC, we do the following. The dealer computes this F0 hat and F1 hat. For that offset gate, it computes the correlated keys, right? Gives it to party 0 and party 1. And now in the online phase, this is what is going to happen. P0 and P1 are going to agree upon X plus R, where neither of them know R. R was some randomness that was sampled by this dealer over here. So it's totally okay for P0 and P1 to learn X plus R. Okay. Now, if they have an FSS key for computing this F0 hat and F1 hat respectively, note that with that, they can locally get secret shares of Y plus S. So they will get a secret, party 0 will get secret share of Y plus S, and party 1 will get a secret share of Y plus S. Locally, there's no interaction whatsoever. Okay. And now if they want to actually maintain this invariant that they want to compute some other function for which they have a similar kind of correlated key, they can exchange just a single ring element, which is essentially the secret share of Y plus S. And both of them can learn Y plus S, which can then be again fed into the next level of computation. Okay. So FSS allows you to go in this kind of masked values to compute functions that admit this kind of FSS protocols in them. Okay. Okay. So yeah, so the structure looks like this. I start off with some X plus R. If I want to compute F hat, I compute, I get secret shares of Y plus S. I reconstruct, I get this masked value Y plus S. I can feed it into the next gate. Again, I get Z plus T, secret shares of it. Again, I can reconstruct, I get both of them learn masked values Z plus T and so on and so forth. And the nice thing is that, I mean, this protocol is kind of, this structure is compatible with even other secret sharing protocols. If I want to make use of this protocol in the middle of some other protocol, which has the invariant that it goes from secret shares to secret shares, I can do that also, because over here I do actually have a secret sharing of the inputs as well. So I can either go from secret shares to secret shares or mask to mask. I can view it however I want to. This protocol can be viewed in whatever sense I want it. Okay. And the nice thing to observe over here is that the communication is one ring element per gate per party. This doesn't depend on the function. It's kind of this is the interesting thing over here. Right? And rounds is also like one per circuit level. Right? So that's also a very nice feature of this class of protocol. Okay. And it's easy to see, I mean, even beaver triples, you can go from masked values to masked values. It's not, I'll not spend time over it. It's easy to see this. One can do this as well. So if I had arithmetic computation as well, I can plug in all of this as well. Okay. So now let me turn my focus to all types of Boolean computations, which is where I said things are interesting, right? Arithmetic style computations, we know how to do kind of with beaver style pre-processing, but let's see how to do all types of Boolean computations. And here, let's see how the FSS based 2PC, how does it compare with other approaches for 2PC in this particular model, right? When we look at this particular model. So if you look at Gabel circuit, right? If I look at the online cost of Gabel circuits, for those of you familiar, the online communication will pay lambda times bit length. So security parameter times bit length is something that I have to pay. I mean, these are for protocols that are based on like one-way functions, which are efficient protocols. I have to pay security parameter times bit length. Okay? And so the online communication cost of garbled circuits is high, right? Online rounds is reasonable. I can do it with 2 rounds of communication, and that's good, right? If I look at the key size or the pre-processing material that I need to store, that's a garbled circuit for computing that particular function. So in this case, I'm giving the cost for computing something like a max of x comma 0, where I start with secret shares of input and I need to go to secret shares of output. Okay. And so over here, if I look at the key size, that's also somewhat high because it is something like lambda times n, right? That's kind of so security parameter times bit length is kind of what cost I have to pay. And in terms of computation, I need to do, actually this key size is kind of proportional to the circuit size. I'm kind of not talking about that here, but that's the key size that I need to pay. In terms of computation also, I need to pay computation proportional to the circuit size. I need to do roughly something like, I mean, for this particular function, I need to do something like 6n PRF, which in practice with AES, I need to do about 6n AES calls, right? So that's also high for garbled circuits. For GMW style protocols, the online communication is somewhat moderate. It's kind of, I can work at the bit level, and therefore the communication is kind of something like, there is no security parameter that shows up, but there's some small constant that shows up over there. That's something like roughly like 10n or something like that for this particular function that I need to pay. Online rounds, on the other hand, is very high. All these costs that I'm providing is for the depth optimized circuit, if I were to use that for computing this particular function. And so even depth optimized, I would have to pay log n rounds to compute this function. Okay, so this is kind of problematic. The key size is something that's actually low because all I need to do is have AND triples for each of the AND gates that I need to compute. And so again, that's something that's fairly small, right? The computation cost, in practice, you may want to compress some of it and then use the PRFs to kind of expand the randomness that you have. But in theory, actually, all of the cost is actually information theoretic because there's nothing, the online phase is totally information theoretic, right? On the other hand, if I look at FSS style protocols, the online communication is fantastic because I told you it's just one ring element from each participant. So it's only 2n total communication. Okay. Online rounds is also fantastic. It's actually even better than garbled circuit. It's only one round because it's simultaneous one round, right? I don't need to wait for the other participant to send anything, right? So that's fantastic. On the other hand, there are 2 drawbacks over here. The key size is somewhat large. Again, this is somewhat similar to garbled circuits. You have something like lambda times n sitting over there, right? I think I made a mistake over here. This is a lambda n plus n squared. So forgive me. Okay. And the computation is also some amount of PRF calls. So something like, in this case, about 4 times n PRF calls. So something like linear in the bit length number of PRF calls I need to pay, right? So these 2 things are something that are high for these kinds of protocols. So if you look at online metrics, right, FSS is highly appealing because you have like great online communication, you have great online rounds, okay? And so the bottlenecks are all over here in computation and in this key size, okay? So that's what we really want to kind of bring down the cost in these protocols. Okay, so there were like sequence of works that we had. First was in how to optimize key size for fixed point arithmetic, which I spent a little bit of time about. And then I'll also talk about how we worked on hardware acceleration of these protocols so that they can now execute on GPUs as well, and briefly talk about that. And I'll briefly also talk about how we are able to use all of that to do things like LLM inference as well in fairly good time. Right? Okay, so let me talk about optimizing key size for fixed point arithmetic. So if you look at different types of functions that you want to compute, all of them inherently require some sort of comparison that they need to call sequence. I mean, they need to call many, many times. Okay, and so we showed a protocol which had where the key size to do comparison alone. So when I say comparison, I mean like you have, let's say you want to compute the max of x comma 0 and get either x or 0 as output. Okay, so that's what I mean by comparison. And if you look at many common functions which we had to compute, essentially we showed how one can do all of these computes using a single DCF call. By DCF, I mean like the distributed, this comparison function that you want to compute, right? So if you wanted to do something like ReLU, so when I said comparison key size and said max of x comma 0, that was over the integers. Once I move to fixed point arithmetic, the ReLU function is slightly different because it needs to take into account things like wraparound arithmetic, and so that's the ReLU function that I have over here, and we showed how you can do that with the same cost as doing the comparison as well. Things like bit decomposition, we showed how we can do with much lesser number of calls to comparison. Now, where things get really interesting is the spline function. And this is like a piecewise polynomial function. Let's say I wanted to take a value x, and I wanted to compare it with multiple outputs. I want to find out, is x greater than 0? I want to find out if is x greater than 5? Is x greater than 10? And I want all these outputs. If you look at any other type of computation, if I look at Gabel circuits, or if I look at GMW style protocols or anything like that, for each of these functions, I need separate Gabel circuit for it, or a separate pre-processing material for it. The nice thing about FSS is that we are able to show that you don't need any of that. One key suffices to compute all of it. I mean, it's not, in hindsight, it's not surprising. It's somewhat similar to what can be done in homomorphic encryption. You don't need something additional because you're computing. There is some inherent homomorphism, and you can reuse the same key to do this. But that's kind of the interesting thing over here, is that how many other comparisons I have, I can do it with a single key, right? So the single pre-processing material that I need for it, right? That's kind of interesting. And the fundamental observation that we had in our work was that previous works were kind of assuming all of these as being secret intervals, and I'll briefly talk about that. But we kind of, when the function that you're computing is public, such as in the case of max of x comma 0, where the function that you're computing is the comparison with 0, in that case, we are able to make use of a relaxation of this secret intervals. Okay, and because of that, I mean, we are able to get like significant improvements in this in pre-processing size when computing a whole bunch of functions. Sometimes, as I told, like when you're computing splines, this is like particularly useful. For example, we had like a 22x reduction when compared to, like, let's say Gabel circuits, when you wanted to compute like a 12-piece spline, right? So that's something that's interesting. Okay, just one slide on how this was made feasible. So essentially, if you look at the unmasked world, so the clear text comparison that you're doing, let's say you wanted to check whether x lied in the interval a less than equal to x less than equal to b, right? A and B were public to begin with, right? This is the computation that you wanted to perform, right? Now, when I went into this masked world because of secure two-party computation, everything became masked. So I had like an A hat, which was equal to A plus R. I had an X hat, which was X plus R, and a B hat, which was B plus R. And I essentially needed to compute this. I'm skipping over some details over here. There are wraparounds. This is not integer arithmetic. And so one has to be a little bit careful about what this exactly means. But essentially now, if you look at it, it seems like I need to do comparison with private values. This A hat and B hat need to be private because R is private, right? And that's essentially what prior work kind of made use of. It said, okay, this is private stuff, so I need to give a key for each of these comparisons. I need to give a key for A hat. I need to give a key for B hat. But the observation over here is that A hat, B hat might be secret, but B minus A is public, okay? And because of that, what we can do is we can give like a universal key for computing all comparisons. So instead of giving a key separately for computing x hat less than A hat and x hat less than B hat, we can give a single key for computing some x hat less than C hat, where let's say C is greater than or equal to both B and A. So you can think of it as the last point in the domain, right? So I give a comparison key just for that, and some additional terms which are information theoretic in nature. So there's no crypto kind of involved in that, right? And the reason why this kind of universal DCF key works is that if at all I wanted to compute this, if I wanted to compute x hat less than A hat, that is, I want to check if x plus R is less than A plus R, instead what I do is I add C minus A to both sides. So I get x hat plus C minus A on the left, and on the right I get C hat. and I have a key to do the comparison with C hat. Right? So I do this comparison, but this may be erroneous in certain parts. It's not the right thing because of all these wraps around. It's not the right value, but I can give out some correction terms that enable me to correct for this. And that turns out that you can do all of this locally itself. You don't need to pay anything for this. And it's a total information theoretic operation. And you can use the same key to do like any kind of comparisons that you want. Okay, so that's kind of, I think the cool thing about this line of work. Okay, so we'll now move to like, that was all like the theory that we did to kind of build these protocols. And then how do you get like practical protocols for doing something like this? So the first cut was that we took all of these FSS protocols and kind of implemented them. And if you look at something like VGG16 inference on the ImageNet data set using this the system that we built. By the way, every time we come up with a system name for one of our crypto papers, there ends up being a machine learning model with the same name after that. So, I mean, like that's our contribution, I think, to the machine learning community. But Llama came out before the Meta's Llama. We came up with, you'll see in a few slides, we came up with something called Orca, and then there was a machine learning model that came out a few months later called Orca. So watch out for our papers, at least for that. So yeah, so we had VGG16 inference using our system Llama, and we were able to execute this model in about 32 seconds on CPUs, right? Now recall, I told you that on the state-of-the-art hardware, which is the Hopper GPUs, this was like under a millisecond. So we are quite far away from where it is in clear text. But it was still only in seconds. We were able to execute like a fairly large model, a few million parameter model running in like a couple of seconds, right? Okay. Then what did we start doing? We started looking at the performance characteristic of these protocols, FSS-based protocols. Where are all the bottlenecks like? Okay. Now, when you look at the online phase of 2PC protocols in this particular model, they can be bottlenecked by one out of two things. One is network bottlenecks, things like communication or rounds and so on. And this is something that garbled circuits suffers from, or GMW style garbled circuits will suffer from because of large communication. GMW will suffer from because of large number of rounds. So these are all network costs, something that hardware is not really going to help you. Okay, solve. But if you look at costs of FSS-based 2PC, all the overheads are local, computation and so on and so forth. That ends up being like the huge bottleneck. Okay. And so FSS-based protocols are ideal for like any kind of hardware acceleration that you want to do. So that's precisely what we did. We looked at the profile of how the split of where all the costs go in these protocols. And we found that compute was the largest part, followed by the key read. By key read, I mean like the time to take this pre-processing material from the CPU memory to the GPU. That was taking up a lot of time. And then the communication. Communication was really tiny. So this is excellent. We can accelerate this on GPUs. Okay. So that's exactly what we did. Some care is needed in this acceleration. So we need to make sure that when you implement AES on GPS, you use scratchpad memory carefully, you do a better memory layout of FSS keys, etc., etc. But it can be done, and that's what we did. This is work that appeared in Oakland a few months ago. And then now the profile looks very different. Now, if you look at the compute cost, now that has shrunk down. That's also like really tiny. And all the cost now goes into just the memory. That if I want to take the key and move it from CPU memory to GPU memory, all the cost was going in that. Okay. And so because of that, we redesigned more FSS protocols that sometimes paid more in terms of compute, but had lesser key cost, right? So because we had room to play with over here, we redesigned crypto protocols with this different cost profile in mind. So the type of protocol that you may want to use may depend on the hardware that you're actually like running it on to get best performance. And so, yeah, these are some things that we did. I won't go over this. And so now with that VGG16 inference is something that we can do with this system in 330 milliseconds on GPUs. Okay, so now we're getting closer to where clear text also is. In fact, if I actually wanted to run single inference clear text cost, like if I just had one inference that I wanted to run, just loading the model and executing it on a GPU and so on, that takes on like any of these commodity systems, it takes about 150 milliseconds. So, I mean, the overhead of additionally using a secure computation protocol is fairly acceptable. I mean, within 2x of whatever you're anyway paying, which is unavoidable in some sense, right? So I think that's kind of cool over here that secure computation can be nearly as fast as clear text algorithms. Okay, we were also able to train machine learning models. I don't think that's that interesting. And finally, I'll say a few words about transformer inference as well. We were able to scale to, there are some challenges with regards to scale, different nonlinear operations. I already mentioned you want accurate approximations of nonlinearity, which are FSS friendly. We came up with that. And we have recent work that could do secure inference of GPT models like Llama, for example, in a few seconds, right? So that's, it's near real time, something that we can do today. Okay. Now, last like 2 minutes or so, I will talk a little bit about where we are headed in terms of this, maybe this GMW versus FSS story that we are trying to explore a little bit more. So if you looked at the cost that I presented, and now I've included what the costs are for including Orca as well, which was the Oakland paper, we found that FSS style protocols had high key size and had high computation, right? And if you look at if this is a CPU and you have a GPU, and if you have some task where these key sizes can be really large, right? Even for like inference of large models, they can be large. For training, they're certainly large, and they may not even fit into memory. In which case, you may want to then store them on disk. And now it becomes incredibly slow. If your key is like very, very large, it's incredibly slow to bring the keys to GPU and then compute on them. And now it's unclear which kind of protocol you want to actually use if you're taking that entire cost into consideration. And so we did a profile and said, okay, let's consider various settings, whether if the key is already in memory, let's say it's in CPU memory, and let's say we are in kind of a low bandwidth RTT setting, then function secret sharing protocols are actually doing well, right? They are kind of the golden standard, right? On the other hand, if I have keys sitting on disk, right, GMW starts winning because their correlation size is actually really tiny, and therefore moving that into GPU is a lot faster, even though I end up paying more in terms of communication in the high bandwidth setting. Okay. And so if you look at it, GMW style protocols and FSS style protocols stress different parts of the system. So the idea was to kind of say, okay, let's combine these protocols. Whenever we want to run something, let's run a mixture of protocols. And that's what we did, right? So if you wanted to be in a setting where keys are in memory and you wanted to run like either in the high bandwidth setting or keys on disk with low bandwidth, you can combine both of these and you can squeeze out performance even more and get better protocols. And finally, about malicious security. So far, I spoke about semi-honest security, where because GMW protocols, they work with bit triples, you can get really, really tiny correlation size. This is not the case in malicious security. In malicious security, because I need authenticated triples, their correlation size actually starts becoming large. And it turns out that if you redesign the FSS protocols, well, you can have an analogous of FSS protocols combining like speeds like MAC checks and so on into the FSS style thing. If you are careful about how you combine this and use the latest techniques from like FKOS and so on and so forth, if you use that combined with whatever we have for the latest in FSS style protocols, FSS style protocols can actually win on all counts. They can win on like key size, they can win on rounds, they can win on communication. All of that, this style of protocols can actually win in the malicious setting, just simply because GMW protocols no longer benefit from having really tiny AND triples, because you need like authenticated AND triples, and therefore their additional overhead because of that authentication becomes so much more that their key size actually starts becoming kind of worse than what it is. So that's like very recent work, not yet published work that, yeah. A couple of case studies that we did, we have built a platform called Truce that enables this kind of private benchmarking that I was talking to you about. This is available. All of our code is available on the easy peasy repository, but this is like a end-to-end platform itself that you can go try out to do this benchmarking of machine learning models. It's not restricted to inference. We have done other kinds of tasks as well. These are significantly more complex tasks. Things like tumor segmentation, which is a much larger model. So that's also something that we've been successful in kind of testing out in the field. All right, with that, I'll I'm happy to take questions. Thanks.
Thank you. So we have one question for Zoom, and if we have from the audience, please feel free to ask right after. So from Zoom is if you can give more details on the GPUs you use, like what type of GPU, if it's very powerful or not, and so on, and how many.
It's commodity GPU, one GPU. Yeah.
Okay, perfect. Any question from the audience? Please, and please repeat the questions for the audience.
Yes.
So we have a repository, and it seems like is coded in C++. Are there any plans to move to Python? Developers and development?
No, not in the near term. But if you have interest in that, we should chat, and it will be great.
Yeah, and for context in Zoom, the question was porting from C++ to Python.
Yeah.
And is there any other question?
Oh, sorry, I forgot to repeat the question. Yes. Yes.
I was wondering if there's any concern from the company's perspective in like making that public, for example, OpenAI might not want to,
Yeah, great question. So model architecture is not something that we concern ourselves with. I mean, it's a notoriously hard problem. The theoretician's answer is like, oh, universal circuits can solve it. But here, I don't know, like, what would be a compromise. I don't see reasonable ways to do this. And so we are stuck to running like, yeah, where protocols where the model architecture is something that's reasonable to, yeah. Sorry, the question was, what about model architectures? Is that something that you can hide as well, or is that something that in your experience is, yeah, is acceptable to companies?
Perfect. I would like to finish with a very quick one.
Yes.
In the numbers you shared with us, all this is in the LAN setting or WAN setting?
All of it was in the LAN setting. The WAN setting for FSS style protocols are actually not that different, because most of the cost is actually like local.
Okay, so it's still so expensive that
there is a degradation. I'm not saying that it's the network costs are not that tiny that it doesn't affect it at all. But if I'm not mistaken, I think for more than 100x reduction in bandwidth, the reduction in time was maybe 3x or something.
Okay.
It's time. It's
Okay.
not for FSS style protocols. It's fantastic. Like you can run it on. Yeah.
Okay. Thank you very much. This next